As you may know, there are two methods currently available where we measure the fatigue crack growth. The first one is based on the crack width method, and the other one is based on the line interception method, which is part of the crack by package. The problem we had with this is that both require some sort of strain value function, and I was trying to develop a method where we can avoid this. So what we did is we had an experimental investigation with stereoscopic DIC. We measured the area of the crack. Then we placed little crack lines, little deformation lines, and we measured the line displacement and removed the rigid body motion. Then we determined the crack tip using a statistical method, the Chow test. The Chow test can determine discontinuity in a data set based on the square residuals of linear regressions. So we have a measure point, and we have to we draw a linear regression through the data set, then we draw two linear regressions of subsets on both sides of the measure point. Based on that, you get a value which determines the discontinuity. The higher the value, the more likely there is discontinuity. Finally, we want to determine fatigue crack growth. So what we did is we took the first values where we are certain that was no fatigue crack initiated and used that as references. We determined the noise of that and used that as a threshold. So in the experimental setup, we have a custom script based on crack mouth opening compliance. Every 1 centimeter, we stop the test. Sorry, every 1 millimeter crack growth, we stop the test and then load statically to maximum load, take a picture and continue the test in the field. Then we process the data and post-process the ESC data to detect the crack and fatigue crack growth. So first what I did was we get a 3D point cloud, which is difficult to work with. So we flattened that with these situations since it's a flat surface and interpolated the deformation over a grid. Of course, that's also a lot easier to work with. Then we take a look over one of the measurement lines, and here you can see the widest deformation with the rigid body motion removed. As you can see in blue, the first line measurement has a almost linear line, and then you get a hyperbolic tangent. And when we calculate the Chow coefficient over these measurement lines, you can clearly see that the crack tip is located. Then we stick all the measurement lines over time, and you clearly see the crack developing visually. But then, we still have to determine when it's actually cracked. So when we take the noise, we calibrate based on the noise, and we detect that way the fatigue crack growth. So we have crack path based on the Chow test. We set a threshold on the mean plus 3 standard deviations of noise, and I'll show you that that works. So first we have the crack path. As you can see, it's not perfect. In the beginning, we have some deviation. That's because we still have the noise is slightly into the measurement field. Plus, there's some plasticity which interferes with the initial measurements. Then we have one outlier which we can attribute to the back face of the strain of the crack gauge. And finally, we look into you can see that the fatigue crack growth follows the crack gauge and you have single compliance. There are some things we can see from here. One of them is that somewhere around the 23rd image, the CMOD compliance deviates with the DSC and the crack gauge deviated from the CMOD compliance. And as we have 1 millimeter steps, sorry, I am skipping one step now. The CMOD compliance is no longer valid in that region because to plasticity. The crack gauge is measured every 1 millimeter. The measurements are made every 1 millimeter step. Not the crack gauge is not measured everywhere perfectly. So in some steps it skips the measurement because it ends right before it breaks, for example. But when we look at the noise, when we set the threshold at mean, you can clearly say that the results do not make sense. But if we add a standard deviation above it, it already starts forming a line, but still overestimates the crack growth. And as we increase the threshold, you can see that it starts to become more compliant with the CMOD. And here you can see that between 3 and 4 standard deviations, it converges. So to conclude, we have here a framework in which we can detect the fatigue crack growth based on the displacements. We use the chow test over fiddle strain ranges to detect crack. The threshold of the chow test is quantified based on the first measurements where no crack is available. And in the beginning, the results are similar to the CMOD compliance, and in the last part, it still follows the crack rate, so we can assume that it works there as well. And we do not need any form of external calibration to make it work. So this was a fairly basic setup. There's still a lot we can improve upon it. First part is that we still need to understand how the parameters influence the results. So what are the optimal DRC settings? How big do we need to the subsets in the chow test have to be? And what are the best reference photos to make the system optimal? For the rest, this test is performed on AR60 railway steel, which is a pretty brittle material. So we should test it on the ductility because plasticity might interfere with it as well. And for the rest, we have to take a look at mixed molding, complex geometries, and different steel types to see if it works. So thank you for your attention. Are there any questions?